Welcome from Berlin, Hans Hübner.
Thank you for the nice introduction. It's only a few Common Lisp libraries that I maintain, so I need to be a bit more humble. But I want to talk about identity in a world of values. That's the title of my talk, because I have been interested in persistence in programming systems for a while, for like a few decades, and have written a lot of code that was concerned with making structures persistent and dealing with programs that restart. And this talk is about how persistence in the traditional sense can be achieved in Clojure. It's a bit unfortunate that Clojure programmers see persistence as a word in connection with data structures, because persistent data structures are really something different from persistence across program restarts, which might confuse some of you. So when I talk about persistence, I'm using the word to describe how data is made accessible after a program or a system restart. So what is persistence and why is it a problem? The programming languages that we use typically are concerned with in-memory data. So they operate on main memory. This is core memory as an example of memory that is directly accessible by the processor. And one typical aspect of working with main memory or with core memory is that you cannot rely it to be available after a reboot or a system restart. The other aspect of directly accessible memory is that it's usually more expensive than other memory. But this has kind of changed in the last few decades. So when our programming systems were invented, Lisp, for example, or Fortran, or any other language, the presumption was made that you had your main memory, and that was what your program operates on. And when you need to store your data, you needed to go to a different medium. So traditionally, you had disks, and the defining characteristic of disks or of secondary storage is that it's much slower and usually also addressed in different ways. So disks have blocks, and main memory has single bytes or words that you can access. So accessing durable storage was something that, or is something that requires different mechanisms. You need to serialize your data, then you write it to a file. You need to deserialize it and read it back in. So there's an explicit step between your program and your durability. Now, we can look at programs of different scale, and what I want to do first is look at small programs that deal with small words. It could be even big programs that deal with small words, but oftentimes what you do is you operate on, well, or what some people do, maybe I do, is operate on small data sets, like a few kilobytes, a few hundred kilobytes. And the question then is, how can I survive program restarts with a data set that has a few tens or hundreds of kilobytes? So one way to do it, and this is a very common thing, I would say, is that you implement your persistence in your web stack. So you have your web request, it comes into a bunch of middlewares, and you implement some form of identity mapping, so that your request is mapped to some persistent entity that you want to store later. Then you have a persistence layer that writes it or reads it. You have some more middlewares and your own program. And this is really a strategy where Clojure as an environment has a lot of neat tools that, or only 3 neat tools that help you achieve that, because you can read data, you can print data, and you can use that to your advantage in a setting like this, where you have a well-defined entry into your program and a well-defined exit out of your program. So at entry, you can read your data, and at exit, you can print your data. Which can, well, and I have to apologize. Actually, short detour. I wanted to be the person who has a perfect Windows-based presentation, and now the Windows machine just totally failed. And now I'm on a Mac, and it's fast enough and everything, but it doesn't have the font that I had on the Windows box. So please accept my apologies for the bad rendering here. I hope it's legible anyway. So, going back to this idea of having a small word where you enter your program, you read your whole data set, you perform whatever you want to do, and then print it again. The first thing that you need to do is you need to know what is it that I'm operating on. And in this toy web application, I just use a client header that tells me who's my client, what is my world, and that defines my database name. And I attach that to the request, and then in the middleware that reads the database and writes it, I use that database name to read the database, then call the handler, and then write it out again. And there's no database here, and it's a very, very straightforward and easy thing to achieve persistence without a lot of mechanics. You have a bunch of files, you can inspect them. It's simple and easy, so that's good. So and in a sense, what this is the read eval print loop in a way, in that you read something, eval your function, and then print it again. So it's very, very Lispy, I think. Now, what if your world is too large? What if you have to deal with a megabyte or 2 megabytes or 3 megabytes of data, and you cannot afford to read and write it all the time? And the first thing that many people would reach out to is a database. So they come up with a data model, and then the next thing is they go to the list of databases that you can use. I am accidentally a Postgres user, but all the NoSQL offerings certainly are in the same ballpark. So you use a database, and the good thing about that is, about a database, is you get the modeling language for free. So you had this. Well, I used UML just to upset you. And of course, this is not the real model. I just wanted to have a toy depiction of what my test data model looks like. So, so then you map it to the language of the database, and of course, this is no longer the object graph that you have in the UML, but now you have to have foreign keys, and you have to specify it in the terms of the database, what you want to achieve in your persistent model. And then you end up with something like this. So it's a data definition that describes your data, and it also describes your constraints. So, for example, we are talking about a bank here. Sorry, so it's a bank, and we have bank account with bonds. People borrow money. So my data model not only specifies what the data is, but it also specifies constraints on the data, and that is part of the database logic. So the database ensures that these constraints are actually adhered to. And then when I have done this, I can just use that database from Clojure, no problem. No problem, except that it's not Clojure. So I have to deal with a Postgres server. I have to deal with data definition language in Postgres. I have my constraints specified in a language that is not Postgres, but Postgres DDL. It's not Clojure, but Postgres DDL. And then I end up with code that uses SQL, a different language, in my beautiful Clojure source code, and that's something that I personally do not like very much. Also, it has all these problems of injecting stuff into your SQL and whatever have you, and well, and of course you can go away with macros and make this more beautiful, but it remains that you are adding a lot of complexity to your application by choosing a foreign environment to store your data, and that's something that I kind of don't like. So I want Clojure. And where I'm coming from is I have been a Common Lisp programmer previously, so one of the things that I liked about Common Lisp was that the object system was completely extensible, so that you could change the behavior of objects so that rather than writing to memory, they could also write to a database or to a file of whatever you want to do. So my ideal persistence environment is an environment where I write my host language code and do not have to reach out to other languages, but do everything in the same language. Now, Clojure is not an object-oriented language, so it doesn't have the notion of identity and value together in an object. So in most object languages, you have something like an identity and a value, and you can change the value of the object, retaining its identity, and that's not something that Clojure provides you with by default. However, Clojure has something that is very interesting in the context of databases, which is transactions, ACID transactions. So actually, Clojure's transactions are not ACID transactions, they are SC transactions, because they do not provide you durability, but they have all these properties that transaction systems have. You open a transaction, do a bunch of things, everything is isolated from everything else. Your change to the global state in the transaction is atomic, and it's also consistent if you choose to program in a consistent fashion. But yeah, I'm stretching it a bit, but this is where I'm getting it. So how can we add the D to Clojure's transactions? That's what I'm trying to do. So Clojure's transactions operate on references. They are called refs, and within the context of a transaction, you can change the values associated with individual refs, and then the transaction system of Clojure makes sure that all the changes to your refs are committed in one step to the global state that the other transactions and other threads see. And you also get isolation in that one transaction doesn't see the uncommitted state of other transactions. And the nice thing is that Clojure doesn't only provide this transaction system with refs, but it also provides a way to hook yourself to the end of to the successful execution of a transaction by the way of agents, because agents receive messages, and the message is only sent when you are in a transaction, when the transaction commits. So at commit time, when your transaction successfully commits, all the messages that you send to agents from within the transactions are sent. And this allows us to come up with a scheme where the transactions at the end tell the global state, where, the logging agent that we have to log the individual changes to the global state to a file. And this is how we achieve durability here. Now, how does it work? Refs in its own only provide you this mechanism that is controlled by Clojure's STM system. But what I also want to have in this system is identity. So I want to be able to refer to a persistent object by the way of an ID. So my persistent ref record, implements the IDref protocol, which is used to dereference something, and adds an ID that is generated. And then you can create these IDs in your transactions and associate values with the transactions, and each of the objects get an ID. And what you can also see on this, this persistent reference mechanism basically implements what bare references have as well. So you can create one, you can set a reference from within a transaction, you can alter it using a function, like you would update something, and you can look up an object by ID. And this then gives you the basic object for persistence, the persistent object ID idea that I want to implement here. Now, everybody is talking about specs, so I don't need to talk a lot about it. But here's how we have the same data model that I explained in the Postgres slide, implemented in specs. So you have accounts, you have bonds, you have references to bonds, and the same thing basically in a different notation. But I would say it's not terribly clear, in particular, given that with spec you decompose your schema into very small items, and I would say it's not as clear as many other schema definitions I've seen. But anyway, so it works well, and you can have functions that check whether something is within your expectations. So it's like the same thing like the constraints that we have seen in the other model. Now, how to actually change your global state, and for this I invented a macro that is called DevTX, which attempts to be the same as a defen, but it's an impure function in that it changes the global state. And a transaction declared with DevTX is wrapped in the code that performs the logging to the global transaction log, which we will see later. Now we can implement a few functions. Make account creates an account. You can see here is sets a name, balance bonds, and a validator, which makes sure that always when the state is changed, the account is still valid in the terms of the spec schema that we have set up. And then deposit and withdraw, everybody knows how to interpret that, I guess. And then here's something that would be much harder in a value-based system, because the bonds reference other persistent objects. One bond is issued by someone else, so there needs to be a reference to another person from within the persistent model. And what you can see on the bottom is that repay calls withdraw and deposit, so it's calling transaction in a nested fashion, which you will see here as being important, because only the top-level transaction is then actually locked. This is the wrap transaction function that is called from within the macro to make sure that the body of the function is called, and then the log is written at the end when the transaction successfully executes. Now, I'm skipping over the log because I'm running out of time. But for one thing, so the log again uses the Lisp mechanisms of Clojure to print the name of the function and the arguments that were given to it, so that it's persisted to disk. And this is again like the same thing, read print. You will see it in the end. So here's a test that does something to the bank. It creates accounts. It deposits something. It borrows. It checks that exceptions are thrown when the schema is violated. So this is just a sample. And what this will look like in the transaction log is this. It's just the invocations of all the impure functions that are being called, and you will notice here that there is no functions no explicit persistence going on. It's just impure Clojure functions that are being called. Now, restoring is also very simple. So we open the file, and then we loop over the expressions, and these are the expressions. And in the end, you will end up with the same persistent state that you had when you originally ran the program. So this is Lisp again. It's read, eval, print. And I found it pleasant and easy to implement. And what I like about this whole scheme is that it requires very little infrastructure, so you can just run the program without having to deal a lot with setting up a server or doing stuff like that. So where is this going? Actually, it was more an excursion into how Clojure can be used to do the kind of things that I would find easy in an object-oriented language or in object-oriented Lisp. I must say that some things in Clojure, when you go to the bottom of things, are not that easy. So, for example, the transaction log really looks very convoluted because for reasons that, I mean, I can understand if I think about it long enough, but I don't really like. You cannot get the fully qualified name of a function because there is no symbol associated with each function in Clojure, which is different from other Lisps. So we end up having vars that are then found using the Clojure class loader, and that's maybe the price of a hosted language. So some of the things were not as easy as I hoped them to be. Also, the print-read duality is not as well defined in some areas. So, for example, when printing readably, you have to define functions that are not documented. Overall, the documentation is not very great. But that's really small gripes that I have. So in general, I found this a pleasant experience, and the whole thing is very, very small and can be inspected if you want to do stuff like that on my GitHub. And that's all I have. Any questions?
So we asked for questions.
It's a questionless conference. No questions at all.
Oh,
there's one. Yes.
Coming up.
Hi, I'm just wondering, did you put that into production anywhere? Because that stuff you printed and you logged was like totally dependent on the state of your system in terms of the code you're running, because you're dereferencing the function, and if you change the function, you're getting completely different state of your system.
Of course.
And that's
yes,
the thing I'm wondering.
Admittedly, this is not in production anywhere, but the system that this is modeled after is. So I have run a similar system written in Common Lisp that does transaction logging this way for many years. It's still running, and it doesn't provide any problems to me. And the thing is, I mean, databases do the same thing. You just don't see it. And then you can look at the database vendor if it doesn't work, but still it's the same thing, and there's no magic in there. So I like having control over my tools. So why not just do it directly? I mean, it's similar to this first mechanism where you just get the ID, read the file, print it again. It's that simple. There is nothing to it, and the Clojure mechanisms really are. I was so pleasantly surprised to see that the sending to agent is connected to successful commit. That's what you can do. So of course it requires a lot of understanding, if you will, or some understanding. But then it's not that much of that much stuff to learn, right?
Doesn't the startup time of the process grow linearly with the number of transactions?
Absolutely.
So is there you know, are you
Absolutely.
thinking of adding snapshotting or something like that?
For this Common Lisp system, I do snapshotting, and I planned to put snapshotting code into this too, and that really the reason for having a separate persistent ID and that you can serialize is to support snapshotting. Otherwise, you could just as well use your own internal mechanism to avoid serializing all the values all the time. But when thinking about this, does my startup time grow linearly? It is really useful to think about how much time your transaction code actually needs to do the things it does. And if you run a few hundred or thousand transactions a day, maybe the startup time of a second or two is not really what you would be concerned about. You are totally right, but in my experience, it's a bit over. It really depends on the real system, not on theoretical things.
One more question. Okay, then I would like to thank you again.
Thanks.